Yeah, he probably like jumped backwards over a broom onto like a glass or something. He's a witch.
Alan's gonna save the day.
Oh, I heard broom witch and stuff. You guys ready to celestial theodolite?
Let's do it.
Get it?
All right, let's do it. Start event. There's already an event active. Start anyway? No, it doesn't work that way. 1 second. And start. All right, 1 second. Gotta get the stream going, and then we'll begin.
Thank God Alan saved us from almost the second SE fear mongering session of the day.
Uh-huh.
Oh, what was he fear mongering you guys on? Nuclear bombs or something crazy? I don't.
China.
They want it, bro.
China.
They want it. They were begging for it.
Missiles.
All right, the Chinese nuclear bombs or something. All right, I'll be right back. I'm going to go roll the intro, and then we'll get into the Celestial Theodolite update number 26.
Yeah, we're gonna be like in senior citizen homes and shit. This guy's gonna be on Celestial Theodolite update number 1842.
Yeah. How many is it now? 20? Holy shit, 26. Nice. Get ready for a troll attack.
Yeah, I think we should get Glober Whitsitt back, honestly. He'd do a much better job at steel manning the opposition, so we can have a worthwhile discussion. Glober Whitsitt was the man.
I mean, I don't even know why we're talking to these guys. Can't Chat GPT steelman the globe model perfectly, or
Just wiki it, bro. Just wiki their opinion. As simple as that.
I gets confused with celestial and terrestrial refraction coefficients, especially when the Globers try to use them.
All right, hello and welcome, lads and ladettes, to Celestial Theodolite update number 26. The last couple of episodes, we've went over the fundamentals from the ground up, so the basic principles of occlusion, how occlusions are a physical process between the intersection of the light and the physical object that's doing the occluding. A refracted image does not occlude light. There is no convergence of the light rays on that image, so there's nothing to actually occlude it. So we're interested in the physical intersections here. I put one of the biggest updates to the spreadsheet since we made it over the last week or so. So we're going to be going over some of the updates to that and the actual data from the measurements. So now that we've been over the fundamentals on how everything works, and we've related angles to time and occlusions and all of that, we're going to now go over some of the data points and then look at the graphs that were made off of that. And we also have error bars. So we'll get into the error analysis and the tools that were used for all of that. But just to kind of run us through the basic premise again, we're using star occlusions to derive the physical elevation of the object that did the occluding. And we can also derive a distance off of that occlusion time by knowing one of the other known variables. So here we're kind of reversing, we're recreating the triangle that created the occlusion, so to speak. And if the Earth is a globe, that triangle will be a specific size and it'll relate to a specific time because of the geometric intersection relationship. And what we found is that through some updating in the spreadsheet, we found that an offset that was in the spreadsheet before, but it looked like it was kind of circularly connected to the flat Earth prediction, actually turns up as an error in the globe Earth, being when you independently derive everything from the globe perspective based off of the occlusion angle, or that occlusion intersection difference.
What do you mean by circularly connected? A circular argument, or just a circular?
It was just mathematically circular. So it was like it appeared as if the answer was dependent on like a flat Earth variable that it wasn't. You know what I mean?
Well, this was specifically using like the arctan to get an angle and then using that angle specifically to get the tangent. So you're just doing like the inverse of your function back and forth. That's how circular it was in the beginning, right? So we try to outside and independently recreate that.
Yeah. So by doing the the original circular version of it is kind of shown here, where you can see that the amount that they go to derive for physical elevation comes out to be, or like it's missing a little bit, but it's missing Earth curve for them. but that's to be expected on how that works for the physical elevation there, because they're missing 200 meters of drop over distance for that. So it works out like that. But then this 200 number, this 200 drop over distance ends up coming up again in the difference in elevation between what we derive versus what the globe derives independently off of their occlusion. So when we subtract these two together, we're left with 200 meters. So every measurement that we're going to go through tonight has an error on it that is essentially globe drop, and whoever has the least amount of that error in their measurement is the one that is closer because of the geometric intersection. So in other words, if the globe was off by 11 arc minutes on this intersection and we were only off by 2, what this is going to look like is this 160 here. If you add this 160, this is how much they're off on their measurement. If you add that to ours, you get 200. You get the drop over distance. So that's what that's going to look like every time. So if the Earth were a globe, these should be reversed. We should have the intersection offset of 11 arc minutes. They should have been closer to 2 arc minutes for their intersection here for 217. So like the physical elevation of the mountain, if you were an observer looking off at a mountain, they would predict 217 as the physical elevation, and we would be off by the 11 arc minutes. These would be reversed. But what we're finding throughout every measurement is that flat Earth is closer and the globe Earth is off. And then the argument has been from the globe that, well, that's just coincidence. There's actually astronomical refraction, and we want to use it from the observer location. So we also included in the analysis at the time of occlusion the the apparent position at the observer location, so we can analyze whether or not that the starlight coming from that is even intersected with the geometric peak or not. So we've got a fresh look on the analysis now, where there's no circularity in between the two, and the offset actually is the difference between flat Earth and globe. Now these numbers are important here because this amount of curve in between this distance isn't an accident. It's a product of being half of the central angle that the star has to travel over. So over this distance, there's 200 meters of drop. So for 50 kilometers between us and the mountain, there's 200 meters of drop that comes out to 13 arc minutes. So the way that you can conceptualize that is, as the star is moving from the observer's location, its true position, as it's moving from 2 degrees and 33 arc minutes down to 2 degrees and 2 degrees and 6 arc minutes, it should be intercepting by a globe peak here at 217, because that's when they're going to be geometrically aligned. Because for the globe, they say that the elevation angles to the stars are a physical product of where they're located on the globe, and only curvature between you and the star essentially would cause this angle to occur. So this is the physical angle at which the star's true position would have intersected with the mountain peak for the globe, and that time that it comes out to have been would have been 6 p.m., 42 minutes, and 4 seconds. But the star didn't intersect there. It was allowed to keep going, and as it got further, it finally got intersected at 2 degrees and 31 arc minutes for the and that's with respect to where the peak is at now. So that's how all these times and everything relates. So we have the actual occlusion time, and we just subtract that timing from the timing difference created from our prediction, and then the globe does the same thing for their prediction, and that's how we're getting all these numbers and times. That's how we converted everything into numbers and time. And then real quick, for every peak, we took some stars and we took a couple second intervals and then broke that down into half seconds. And for every half second, we have the star's vertical drop rate plotted out. So for every latitude, it's going to be slightly different than following the 15 degrees per hour. It's going to be a little less. So we have all of these all plotted out for every peak here. Let's see. In the data table, it's this number here, this drop rate. So instead of 15 degrees per hour, it's like 11.97, 11.58. Oh, that's a close one. But yeah, these are the vertical descent rates, and you can confirm these in Stellarium and all that. So it's not like we just made them up or something. It all plots out exactly. So when we've gone over Pike's Peak here. So over here, like a lot of this is, looks like a lot, but I'll go through it real quick. So the light pink section up here is the idealized globe and the idealized intersection there. So whenever the star's true position intersects with what the globe physically predicts, that's where we get our snapshot here. And then the darker pink here is the independently derived stuff off of the occlusions. And then all the math that links how we solve for the central angle stuff for all that is down here. So there's 2 central angle sections. One's for the idealized globe and one's for deriving the angles off of the occlusion time. So the other one's entirely occlusion angle based. And then that's how we get our distances and elevations for the time of occlusion for the globe. So none of them are linked to flat Earth anymore. And there used to be a section here where the spreadsheet was driven by subtracting the half of the central angle from the flat Earth prediction to get what the globe predicts geometrically. Now this holds true. It's not like invalid to do that, but there was some complaints, let's say. So I changed it up here. So whatever the angle that is predicted by the globe, you can use the independently derived angle from for solving for gamma, or half gamma rather, or you could do the flat Earth method. And then when you go in here to predict it, you could put it in globe Earth mode or flat Earth mode, and you can see how it changes. It changes by 1 meter for the thing. So it's,
You know, I forgot we started out by doing that. That's the actual Heffron method, which is a flat Earth prediction minus half of the central angle method for the globe prediction, so that you're not, quote, straw manning the globe with a triangle, right? Even though the linear distance is like difference between is like 13 centimeters over that, so that's why you can approximate it with a smaller triangle. But we started out by doing that, and the globe lads were like, no, that's not it. To do it fairly, you need a smaller triangle, which is how we did our current method with the other smaller triangle. And then our Czech lads were like, haha, you can't use triangles, you should use central angles. So back and forth we go. Good thing we have both methods, and good thing that they actually come out to the exact same prediction.
yeah, well said. So yeah, when you go through the math for the globe side here, all this is done through spherical trig in relation to gamma, and then all of that is derived down here through the A, B, and C, which you can find the proofs for that over here. So when we talk about central angle and half gamma and all that, this is what we're talking about like geometrically. So if you were to take a look at this in terms of like, we have an observer here, we have the mountain peak over here, this curved line here is our arc length, and the curvature of this arc length is going to be half of the full angle from peak to the observer here. So when we talk about things transiting the sky, the relationship is like it has to move 90 degrees in the sky to go from your zenith to the horizon. But the way that you perceive it, you only perceive half of that function. So you always perceive like the half gamma side of it. So you never see the full sweep of it. But anyway, that's the relationship there to how the gamma relates to Earth curve and how this relates to the timing and stuff. So if the physical elevations are predicated on this globe rotating away from a star that's essentially fixed in the sky, then its physical elevation is going to change based off of that rate of change in relation to the angle sweep in between you and the target. So that's why we can do let's see. So we can do things like the refraction correction for this. The way that it works out is half of it's basically the central angle. So the curvature between 50 kilometers is 13 arc minutes, but then they have 12 arc minutes of refraction. That's essentially like 1-to-1 offsetting the Earth curve, because it has to be, they're like, well, why is the apparent position higher than what it should be? Well, it should be lower by 13 arc seconds because of it just went over Earth curve as a physical elevation change, but there actually wasn't any, so it's still at a higher elevation. So anyway, that's how that relationship works with the refraction. What we're going to notice is that the refraction amount is almost always the central angle amount, or pretty close to it, or over it. So we've been over our first measurement here for Pikes Peak, and we'll take a look at some air bars for Pikes Peak as well. So as I mentioned earlier, that we have air bars for all of these. So we'll go over those real quick. So the elevations and distances are of course derived from the occlusion angle, and the known distance. So we take one of the other known variables and then do the trig function to get the corresponding angle and or distance or elevation amount that we would need. So when we do the same thing here, based off of the occlusion and the distance. So this gives us altitude, and then we have one for determining distance, which is altitude of the mountain peak times the tangent of the occlusion angle, which gives us a distance. And then for the globe, we do cosines to the radius and gamma and all that. So all those are not circularly linked. So anyway, when we derive elevations here, our target is noted in orange. The plus or minus air bars are created from doing a normal Gaussian distribution, which is essentially the mathematical equivalent of saying that 68% or 64% of your measurements are going to turn out like the worst possible min maxes. So it averages, the way that it averages that out, it doesn't give you like a max tolerance like the way that I did it before, where I was just like, okay, everyone gets 1600 meters for distance and 30 meters for elevation. Well, this actually gives offsets for like what the min maxes could be for all that, averages out, does some square roots, and then sums it all together. And then that's where you get that's where we get these air bars here. So this plus 400 meters for flat Earth and plus 474 meters for globe. All of these are determined from from that squared, root squared sum process to give the air bars. So anyway, when we go through the occlusion timings and derive the elevations, we can see that we're closer on Pikes Peak. And then for the distance as well, actually I think elevation, or yeah, distance was first, and then elevation here. You can see that we're closer in the elevation. If you need like a visual representation of what this spreadsheet is supposed to be showing you, this is a way that you could think about it like that in terms of like how close we are and how the globe is off of their mark for the known distance or elevation. So we'll move on now to another peak. Look at the other examples. Are there any questions so far?
Ooh, you know what we should add to the error bar for each peak is amount of missing Earth curve, and then we can show that the graph for amount of missing Earth curve will be exactly equal with the amount that they're off, and maybe that will sell it a little bit better. Just had an idea.
Yeah.
Just add a third mark, the amount of missing Earth curve.
So if we subtract the flat Earth elevation derived from the globe Earth elevation derived, we get the 200 meters of globe curve, and that's how much they're off by.
Yeah, I just mean like to visually represent it. You should also plot a third point that just shows the amount of Earth curve between each of the observations, so everyone can visually see the correlation there. Because we keep saying it, but I think it gets lost.
Yeah, I mean, I look forward to your template diagram, to which I'll then make all the peaks or whatever.
Right.
So for Blodgett Peak, we run into the same situation here where we're going to analyze from the intersection offset. So we've got, we predict 116 for our physical elevation. The star was occluded 5 arc seconds different from that, which is a time translation of 27 seconds. And there for the globe, they predict a 107 physical intersection instead of the 116. And they were off by 14 arc minutes, which comes out to be a minute and 16 seconds in terms of how much they were off. So they predicted an earlier occlusion time by 19:05:40, whereas the occlusion happened at 19:06:56. So off by a minute 16 on that. And then let's see, there was one other thing. Oh yeah, so their refraction amount here, right? So remember, their half gamma is 9 arc minutes, which translates to 100 meters of drop off of that mountain peak, and then their refraction correction gives them 180 meters in lift. Or if you do, yeah, I think I just did the regular tangents for that. So yeah, it just gives, it basically is overcompensating for their but for how much there should be just regular globe drop if there was like no mountain. This is explaining why the elevation change isn't following the half gamma for their drop over distance. So anyway, for the time of occlusion, where they would want to go, okay, well, it's refracted, we're going to use the apparent position. So even in this, they're 2 arc minutes over the physical intersection point. So remember, 107 is their physical intersection. The refracted position at the time of occlusion is 109. It's 2 seconds above the physical object that they say they're occluding. And you got to realize that celestial and terrestrial refraction too don't intermingle. One's coming from the sky at an angle that's traveling through mostly the troposphere, which it's not mixing with the whatever the terrestrial stuff is going on at that layer. They're explicitly separate layers. So you can't just be like, oh well, it got occluded at this time because it was because the true position was lower than the peak, but there was this much refraction. Well, you have to use your full amount of refraction. You can't be like, oh, there's 2 arc minutes left, there's 13 seconds left on our 130 refraction amount. We're just going to tap out here at 117. We're only going to use 1 minute and 17 seconds of our refraction. That doesn't work that way. If there was no mountain peak there, it would have to traverse the extra 2 arc seconds to get down to that physical elevation. So you can't do that. So it's still off. Even the refracted position is now off geometrically. It's coming from the sky to intercept something that's on the ground that's above the observer's eye level. It can't be occluded while being over it. That doesn't make any sense. So to continue on with this, we've got Cheyenne Mountain.
How does that not make sense? I guess that last thought was a little bit, I just misunderstood maybe what you said. Can you repeat it?
Yep, I got you. We'll go back to it too. So if the mountain elevation is physically 2 arc minutes, 1 arc minute, 7 seconds, and the apparent position is at 109, it's 2 arc minutes above the physical geometric peak. So it can't be occluded by that. It hasn't been geometrically overtaken by it yet. It's still actually above it.
You mentioned something about the refractions couldn't be, say, commingled or something. You have the terrestrial refraction and the terrestrial refraction and the refraction from the mountain through all the layers of atmosphere up into the sky, a great distance away. Those couldn't be added together.
Correct. The starlight's coming from air that's being affected by the troposphere, and the things that are dictate, like the things that they computate to describe how what's going on with the troposphere, and what's going on terrestrially, which is below eye level, is dictated by a different boundary layer, and it's all has to do with like creating a homogeneous medium based off of a lapse rate and all of that. It has nothing to do with starlight being, you know, multiple meters above that boundary layer. Like it's two separate interactions the way it's categorized. And like I found some history of surveying where they tried to mix the two for geodetic surveying and it didn't work out. They were like, no, you can't do that. There was like a whole thing in the 1700s.
But that, say you had a target with a hole in it at the top of the peak, and the light would come through it. It only would shine through it. Like some of those structures, like the pyramids and other big structures around the world, historical structures that have holes that line up with certain stars, or even the sun. And the sun suddenly only went through this one hole at one particular time. If you were down below the mountain and you saw this happen, there would be refraction that is happening between you and this mountain that is, you know, many miles away. That would be independent of the refraction that happened between the sun hitting that hole and the actual light source. Would you not agree with that?
Yeah, but that doesn't change the fact that in this scenario, the incoming starlight is geometrically above the peak still. So it can't be occluded if it's geometrically above the peak for the observer.
If it's going through refraction from that light source to the peak, it would be loomed up because it's going through a differential medium with a, you know, not such an acute angle of attack, but angle of incidence rather.
So if it's geometrically above the object, it's not going to be occluded. That's the whole reason it's visible in the first place, no?
Well, yeah, if it's geometrically above it, then refraction will just make it more above it.
Right.
But that's
so at the time of occlusion, it's 2 arc minutes physically above the peak. So it hasn't traversed the difference of the end of the starlight to the peak yet. So it's still above it. So they're just saying that, oh, well, now it ends 2 minutes early because it's actually 2:07 below this now. And it's like that doesn't work. Because for every instance, like for the sun, like I was going over this last week with Guy McGuyerson, when the sun is setting, they say that the true position, you know, it eventually, you can even do this with stars and stellarium, you could set the apparent position to negative, like the smallest negative you can get it, like -1 arc second, and then turn refraction on and off. The full refraction amount is what's lifting it to that zero baseline. So you don't get to be like, oh, we've got 2 minutes left over, we'll just round it off to not that. Because if that were the case, then like that contradicts with other answers of how it would work with refraction for things. So it's being occluded above the peak that doesn't geometrically track.
So it's like they're saying refraction is blocking the light or something.
Well, they're not even saying anything like that. What they actually try to do, low key, is if we go back to Pike's Peak here, they'll add the terrestrial refraction to the mountain peak, which makes it go from 217 to like 219, and they'll be like, oh, it's interacting with the refracted position of the peak, but that's an untenable position. We've shown many times here that refracted images don't occlude light sources because there's no convergence of the light rays behind the fake image, so that's not even a tenable position. But that's low key what has been proposed, is that this method matches the geometric intersection of the apparent position, but that's not, that doesn't even cause an occlusion. That would cause the star to like linger at the peak of the mountain, to like kind of be inside of it a little bit, because 2 arc minutes of the mountain isn't physical. So that doesn't work out either. But that's what they try to say.
It's obstructed because it's not obstructed.
Right. That's essentially the takeaway, because there's only one occlusion time. So if they have leftover refraction, their only option is to just be like, oh, it's just coincidentally matches flat Earth, and the leftover refraction that it would still be lifted over just happened to that happens to be it for every measurement. Like that's, borderline preposterous. But looking at it from Cheyenne here, that's what we were just looking at with was it Cheyenne? I think so. Yeah, they were over by 1:45, which comes out to be 12 seconds for their physical intersection for the apparent to what they geometrically predict. So even giving them that benefit, they're still off. And then we go down to Blue Mountain here. So we got a distance of 49,000 meters. And what this comes out to is we're off by 3 arc minutes on our intersection. The globe is off by 17. It's a 2-minute difference there. Whereas we have 27 seconds in difference from our prediction. The refraction amount comes out to be 2 minutes and 13 seconds there. So a full 18 arc minutes of lift over their central angle drop of 13 there, which gives them almost 200 meters of drop. So none of their measurements are manifesting as an occlusion that corresponds to a globe. And then even their refractions is off where they're above the peak at the time. So they would predict a later time because it still has to set into the peak. It's still to be geometrically occluded. So that doesn't work for them either. And they've already missed their physical intersection by 2 minutes. And then when we subtract the difference again there, so we're off by 56, they're off by 50 or 250. Subtract those out, you get 194. You get that central angle drop over distance. You get that amount that was able to be traversed because there wasn't a mountain there to block it.
Didn't our buddy Rolling My Boulder have questions on this last time? Wasn't he trying to go through the process faithfully and in good faith, I think?
Who's that?
Rolling My Boulder here? I think he's here.
I have no idea. Anyway, we got Mount Rosa here showing the same situation. Now this time we're off by 43 arc seconds, which is one of the smallest ones that we've got in terms of a difference for intersection here. So we're only off by 10 meters on that, and the globe is off by 188 meters. When we add those together, or subtract that, we get 178 meters. That's their drop over distance. The timing difference between our two predictions is 5 seconds and 1 minute and 24 seconds for the globe. At the time of occlusion, they're refracted up. Above it. They're refracted up almost 2 whole arc minutes above the peak, so they still need another 12 seconds for a geometric intersection with the apparent light and what they would perceive as the actual geometric peak for them. Going on to Green Mountain.
Is the globe factoring in looming up of the mountain as well?
Yes.
No.
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 Don't they say wasn't it the 2 degree 31 minute 3 second thing?
That's the angles based off of the geometric occlusion for like what the globe would predict. There's no looming mountain effect. That doesn't really.
A looming mountain couldn't block light.
How so? We just went over physical intersections to cause the actual occlusion. So all we're interested in is the actual, the actual geometric angle though is what causes the occlusion.
The idea is that the light from the mountain peak, by the time it reaches the eye of the observer, it'll be looming up, just to say simply, looming up. Now, it could be an insignificant amount, I don't know, but it would be more often than not looming up, which means if we're getting into really small, precise measurements, to just look at the light of the mountain, but use the pure geometric and not the post-refraction would not be fully accurate. Not saying you're not accurate, but that's just what I'm thinking. That's all.
Aren't we talking about an occlusion, though, not light from something?
Whether the light's there or not, what is not there and also what is there will be refracted.
But
we're focused on the occlusion.
Isn't refracted anymore because it got occluded, though. So huge distinction there.
If you sit there and look at some light that's above a fence and you see it, neighbor's light on his wall, and you can see it. If you move your head down, it'll disappear. Right, it'll go away.
Right, it gets blocked. Right, it gets blocked by the physical thing that's blocking it. Yes.
If I go up, also now if there was something between me and this, if I had some liquid nitrogen or something, a pot of it sitting on the top of the fence, and I couldn't see it for a second, I might be able to see the light over that fence just by having liquid nitrogen.
So listen though, the problem with this hypothetical
is
it is true, but you're introducing an entirely different medium to provide a boundary interface for the image that's behind the thing to be projected onto, to be lifted up for you to see. That's not what's happening here. We have, I'm just trying to let you, we're dealing with a mountain that's occluding a star.
I know,
so there's no one up there with liquid nitrogen.
No, the liquid nitrogen is only to give an example that we can take something that's going from us to the fence, and at the fence position, do something with the atmosphere to make the light bend. No different, even though it's spread over a period from us to the mountain over that period as well, because the light is traveling through a differential medium at an angle of incidence that allows this differential version of refraction to occur. If you don't think that's possible, then I think we lose on the globe side, and you guys win because you're just denying something that we think happens. I see logically tried to.
What you're introducing though isn't what happened with the mountain in between us and the starlight. So while I don't disagree that what you're saying is possible, and there's even videos of it that show it, that's not what happened, and it has nothing to do with this.
Well, I would agree that the light at the top of the mountain should not change position in your field of view. I would agree that the mountain has loomed up at some angular measurement.
Even if the mountain has loomed up, the part that has loomed up is non-physical, so it's not going to actually cause any occlusion. That's why we're only interested in the time that we no longer see the star.
Okay. I think I see the problem, and I think you're saying that that's not the case. But I would have to say emphatically that it could be the case, because even though it's loomed up, that physical object and everything that it can do will be loomed up, will be higher in your field of view by some fraction of a degree.
And none of that could actually physically block a star because the light rays don't actually converge to what's being lifted up. So that has nothing to do with anything. It's not a point of contention.
All right, then go back to the fence. So I want to, so in my mind, maybe I'm confused. I just want to talk about it. So I have this liquid nitrogen bar or pool on top of the fence, and I put it there, and suddenly that where I couldn't see this light before, I now see the light. Or let's say the pool was there and I could see the light. I move the pool of liquid nitrogen away from the top of the fence, and the light disappears.
But you're adding something into reality that isn't reality. So just
the reality
stop.
is the equivalent, he knows what I'm going to say. The equivalent reality is the distance between me and the fence is equal to me and the top of the mountain. That light can bend just as much as a net effect as just doing something with the atmosphere on top of the. I'm trying just to try to disqualify the assumption that this loomed object can't occlude something. That's where you're kind of resting your head on that concept, and I think that's incorrect.
But you're adding liquid nitrogen. That's not even reality, bro.
So no, I'm adding something that is not real, that is not tangible, to change the light's path from you to the top of the fence. So it is equivalent.
Zanick,
you can try to tell me what's not.
Zanick, you're introducing something that's not present in any of the measurements to say that hypothetically this could be happening. That's not happening now. So we don't need to. We don't need to discuss. We don't need to conceptually discuss it any further. Because that's not even what's happening.
But you're making a statement that says that this thing that's loomed can't block something. I'm giving you an example of where it would be. So I have a liquid nitrogen plate or something that's right on top of the fence, and I see this light on the neighbor's house. I'm 50 feet away, and I'm 300 feet away.
You're introducing a completely different thing, bro. It's not even analogous.
Help me understand, because I don't quite understand. So I want you to help me. I don't want you to say it's different. I want you to say why it's different. So
you know what I want you to do? I want you to keep repeating the same thing over and over again.
In 5 seconds. 5 seconds. So I got the little plate, and I see the light. And then someone goes over there while I'm looking at this light. I can totally see it, and moves the plate away, and suddenly the light is gone. So what I would describe as this plate provided a mechanism for the light to bend downward to the light from me looking to the light. It's bent downward, so the light loomed up. When the plate was removed, the light's path to me went down, and I couldn't see it anymore. Now I know it's not the same, everybody. That it's because it's a physical object. It's the same concept of looming that could happen between me and this mountaintop, or me and this fence.
What you're proposing isn't even the loomed object doing the occluding. You're proposing another medium to lift up the object behind something. That's not even what we're discussing.
No, the fence is hiding the light for sure. It's not anything else doing it. The light is actually blocking the light. It's not. I can't see it. It's not light. My eyes aren't lighting up. My face isn't lighting up. I'm not seeing it. The liquid nitrogen being there, like in other words, having refraction being there.
But it's not there.
Listen, Zanick. Nobody's saying that's not a thing. We're saying that the fence that you're looking at, right? You're saying that if you had like a refracted image of that fence lifted up, that would be blocking light. That's impossible. That's not what happens. That's what's being discussed here. No, it's not.
Because the light can't bend downward through.
Can I chime in? Can I chime in?
Go ahead. Go ahead, real quick, D3.
Hey, think of it this way: you're thinking about a light source that you can't see, and then you introduce something, and then you can see it, right? Think of it backwards, because that's how the experiment works.
Opposite.
Yeah, think of it backwards, right?
No. You have to think of it opposite. We can't see it because we have refraction. Assuming we don't have refraction, then you're saying we introduce something and then we have refraction.
All right,
because
Zanick.
We don't see it. Go ahead.
Tune into the stream real quick.
Exactly. Now,
tune into
think
the
about it.
Go ahead, D3.
Okay, yeah. Tune into this stream, and then think about it backwards, right? Once that refraction is finished, like you can't see it, there's no refraction to account for there. But go ahead, watch this.
So,
I don't understand that
so
statement.
Zanick, what we're looking at here is a physical knife and a glass of water. And we also see from where we're sitting the refracted image of the knife. Okay. When the laser light intersects with the refracted image, it doesn't get occluded. Only when the source of light is behind the physical knife does it get occluded for us on the other side. So we could watch this play out here. If Canva will actually play the video correctly. There we go. So she's going to move it back. So she's going to move it back and forth here. So the refracted image doesn't occlude anything. So the idea that the loomed mountain needs accounting for, it doesn't. All we need to know is when the star isn't visible, because that's when a physical intersection occurred to block the starlight. If the starlight is inside of the refracted image, it is thus not occluded and has to be moved further to intersect with the physical object. You see how it's inside? It looks like it's inside of the knife there. That's
I
what
couldn't see. Can you do the whole thing again with the knife? Because I was trying to, your whole thing went blank, and I had to find a way to get it back up again. So now I got it back in front of me. I see the thumb, I see the red dot, whatever, and I see the knife. So can you go from the beginning?
Yeah. You see the refracted knife doesn't occlude anything. That's all we're concerned with, is when was it actually occluded? What angle was the star at when it actually got occluded?
I think the refracted mountain does need to be occluded for, because what we're observing is a refracted mountain and refracted stars. So we can't just I don't want to say pretend, but we can't just factor in one of the refractions, but then use a non-refracted one to get precise variables. Does that make sense?
I think I see what you're saying.
No, because we're basing it entirely off of the geometric intersections for both cases, because
So you're
that's what
saying-
actually causes an occlusion. Go ahead.
So I see the knife, and behind it, it's occluded. And then you're saying that if you move it a little farther to the body, we're like right there. Stop a second. So there, it's not being occluded by the knife, and it's certainly not being occluded by the refracted image. I think that's what you're trying to say. Like I see the dot, and I also see the knife.
Correct.
But we know the position is angularly to the right from the viewer's perspective, because you're not blocked, because it's not being blocked anymore, because you pushed it for the physical. Hold on. It'll be easier if I just finish the sentence. So you moved it over.
Not for me,
so
though. It'd be harder for me. Sorry, go ahead.
I know it's very difficult for you. So you got the laser light now on the other side, on the right of the real knife, and that's why you see this light. At the same time, you see this refracted image of the knife. Is that what you're saying, Alan?
I'm saying that this.
Just yes or no. So I just want to get a clear understanding what you're saying, because I think I'm trying to.
You said a bunch of different things, and honestly, dude, it's not that complicated.
I'm just trying to like steelman it.
Please don't go any slower or faster. This is all you need to understand. The knife is refracted in the cup from its physical position. The refracted position doesn't block light. Only when the light source is actually being blocked by the physical object, when that angle of intersection occurs, it's no longer visible. So, and that when she's moving it back and forth, she's moving it back and forth between the apparent position. It's not blocking anything, and then when it hits the physical knife, when that intersects, it gets blocked. It's that simple.
Dude, if it was me, Zanick, if it was me, I'll personally allow you to claim terrestrial refraction at 7/6R for each of the distances for every observation, and you'll still be wrong. I hope that can move this conversation forward.
Yeah. Let's put this mountain thing to the side. Let's just keep going with the presentation, and we could all talk about it more in detail later.
I think I understand now your position. Thanks for the example. I get it. I have a response. I'll talk with that later. But yeah, I totally understand what you're talking about. I said that exactly in different words to what you said about the laser beam. It's being not refracted past the light, because it's outside of that glass in the water. You see both the refracted image and the light being on the inside of the refracted blade. It's not blocking the light. So that's what you're going off of. And you have a little bit. Okay, I'll register that. I understand now. Thank you. And I'm going to put that as a sidebar for later. Okay. There's errors with that whole logic, but that example. But I totally thank you.
Yeah. Okay. So while we continue on, what you should do is find some examples of a refracted image blocking light. Because I'm not really interested in your diagnosis of how the logic is flawed unless you can show me a physical demonstration.
A horizon, or a sunset.
Yeah. Zanick's logic is flawed, and that's why he's running with it.
It's not. It's your glass is separate from the laser. It's not going through any differential medium. It sits at it. Let's talk about that later. I don't argue with it. I just wanted to understand, and I appreciate your going through. And I definitely like that glass example, because that made it totally clear what you're basing all this on. And I think I see a problem, but I'm enjoying the presentation. Thank you.
Okay. Well, enjoy. So we got Green Mountain here. Same situation where they're, let's see here, for physical elevation for flat Earth, we predict 107. Globe Earth predicts 51 minutes of arc, and they were off by 15 minutes of arc there for their 51, which comes out to be a minute 42 for how much they were off on their prediction. We were off by 8 real seconds, which translates into 1 arc minute of difference for our measurement. And at the time of occlusion for Green Mountain, they had 18 arc minutes of refraction, lifting their apparent position up to 3 arc minutes above the peak, which has to be descended to physically intersect with the peak, which would take another 20 seconds. So even the apparent position is off by 20 seconds. And let's see, for this one, if you were to add the terrestrial refraction to the mountain peak, they would still be off by 6 seconds. There's still 6 seconds, or there would still be almost a full arc minute above the geometric peak. 55 arc seconds is basically 1 arc minute. Then time-wise, it comes out to be 6 actual seconds. So even if you added standard refraction to the peak and tried to do it that way, it's still geometrically off. Still should take 6 minutes to set into that peak. Or sorry, 6 seconds. So for North Peak, we have a 13 arc minute difference for us. They predict 35 arc minutes of drop over this distance. This is the longest distance for the celestial theodolite for the terrestrial observations. We have 130 kilometers. And for the drop, that comes out to be 35 arc minutes, which is 1,340 meters, which corresponds to 8 minutes of real seconds to traverse that 35 seconds there. And then when we do the comparison for the intersection differences, Flat Earth was off by 13 arc seconds, which translates into 3 minutes. And the globe was off by 21 arc minutes, which translates into 5 real life minutes. And if we go to the predictions here, or for the time of occlusions here, we'll see that they predicted an occlusion earlier at 21:03:14, based off of their geometric intersection of 9 arc minutes for the physical elevation of that peak. And what was actually measured was, 21:08:21, which comes out to be 58 arc minutes for the true position of the star. And that leads us to where we are here. So if you subtract what we're off on Flat Earth from what the globe derived for their elevation, you get the drop over distance there. So we were off by 500, globe was off by 800. So again, let's see, where's Pikes Peak, North Peak? Yeah, right here. So here's what North Peak looks like. Now, because of the distance, the scale, doesn't look as clean as the other ones, but this is the North Peak differences here. So this one's for distance, yeah, and then this one's for elevation. So the difference in our elevation is what they, is basically how much they were off by. And for distance wise, we got 100,000 of that, 130,000. So we were off by 30,000 meters. And the globe was off by 39,000 meters there. So, and that's just a product of the ratio of the triangle when it's, when it doesn't intersect with it cleanly. But we have Getaway Mountain. So here the globe predicts 39 arc minutes of elevation for the peak. We predict 52. There was a 7 arc minute intersection difference between our prediction and what the time of occlusion. And for the globe, there was a 20 arc minute difference, which comes out to be a minute and 55 seconds versus our 41 second difference. And then when we get into the occlusions, they were 2 arc minutes above the peak at the time of occlusion, so they still need another 15 seconds to be lower than the peak for it to actually be occluded. For the globe, if you do the refracted to the geometric globe there, and then for their apparent intersection on the refracted globe to refracted starlight, they would still be 4 seconds off. Houndstooth. All right, so we got 10 degrees, 40 arc minutes for the elevation for Flat Earth. Now, this one was a shorter distance, so this is one of the shortest ones, if not the shortest. So the difference here in curvature-wise isn't a lot, but you'll see the same discrepancy in between our elevation differences and how it plays out time-wise. So there's a 3 arc minute difference in what was predicted for the occlusion, and then that translates into 19 seconds. And then for the globe, they ended up being off by 32 seconds, which translates into 5 arc seconds of geometric intersection difference there. And then with their refraction amount, they would be just over 1 arc minute of the physical peak, which gives them about 6 seconds before it would actually drop below the peak. Someone's microphone is hot. Looking at you, Phantom.
Oh, man.
All right, then we got Old Blinn here. So here we have an emergence. So we actually have to Actually, I think Houndstooth was an emergence too. So you have to flip the signs to get it to subtract properly because it'll happen sooner than what it shows. But anyway, what we have for old Blinn here, we're off by 12 arc minutes, which translates into 1 minute and 25 seconds. The globe Earth is off by 2 minutes, which translates into 18 arc minutes. Their central angle drop for this, or their half gamma for this, is 5 arc minutes, which translates into 39 seconds. And their full central angle sweep over this distance is 20. So what I thought was really interesting is that the refraction correction is actually the same amount as the full central angle drop. So like that's pretty funny because it's another word saying that there's like no elevation change over it as it traverses that due to refraction, because they predict 38 meters in drop over distance, but the 20 arc minutes of refraction gives them 131 meters in lift. So it's like triple compensating for the curve there. But anyway, the differences in prediction and all that are over here. And then for the apparent position intersecting with the peak, well, at the time of emergence here, it was the apparent position was already over the peak by almost 1.5 arc minutes, which comes out to be 11 seconds. So this star would have emerged 11 seconds earlier if the peak was geometrically lower like that. And when you derive or when we look at the elevations derived, we see that the air is still on the globe side here. The difference in what we predict versus what they predict ends up being a greater time offset for them. So still not matching what it should. So our measurement air here minus theirs comes out to be 38. And then same thing for the other Mount Blinn here. Now this one's really interesting because in this case, we derive the same physical elevation based off of the occlusion time. We end up being 1 minute and 9 seconds off. The globe ends up being 2 minutes off. Because this is an emergence, remember, so it should actually be 2 minutes sooner rather than later. I just haven't fixed the signs for it. But anyway, they would predict that this happens earlier because the star is higher for them, and the difference on this comes out to be for the apparent position with respect to the peak. At the time of emergence, they're actually 4 arc minutes over it. So it would have occurred sooner if the principles of refraction work the way that they were saying, where it basically comes out to be 1-to-1 of lift in terms of like, let's say there's 15 arc minutes of lift. Well, the true position has to be 15 arc minutes lower than the object. It has to take up that full amount. And we can see what that looks like in Stellarium when we wrap up here. But they predict that they would already have emerged, have intersected with the peak 27 seconds ago. So the star still emerged with our principles. The physical elevation for rise over run came out to be 52. The globe predicted 41. The star aligned with was 10 seconds off the 10 arc minutes off of the geometric prediction for us, but it was spot on for the physical elevation that they predict with their missing curvature. And then look how it played out airwise. So in this case, we were off by the full Earth curve amount, but they were off by double that. And then subtracting us from them gives this the regular amount. So it's interesting how this played out in regards to the positions of the stars with how they're supposed to be geometrically aligned with these terrestrial features at these times, and the air offsets that it produced for the elevations is pretty fascinating. So let's see here. I think we got one more. We got Varley SE Squamish from Goose. So here we have another shorter distance one where it's 16,000 meters, comes out to be 22 meters of drop for the peak. And then when we derive the elevations for everything, we're off by 24. The globe's off by double, if I'm not mistaken. And you subtract that, you get the drop over distance. We were closer to our target by 4 arc minutes or 31 seconds. The globe was off by almost a full minute or 9 arc minutes for that. And then geometrically for the time of occlusion, we have, was that 46 arc seconds above, so almost an arc minute above the peak there. So another 5 seconds before physical intersection for the apparent position. But 46 arc seconds is pretty close, but still requires a time of transit for that. All right, and that's where we're at with the latest analysis. So all the error bars for everything can be found here. And this just is mapping the expected position or distance or elevation versus what was measured. And then again, if you subtract the difference between the two in elevation, you get the expected drop over distance. And the air side leans more on the globe every time.
Ooh, is it true that you're currently strawmanning the shit out of the globe? Because that's my only objection. Are you currently strawmanning the globe super hard?
Let me check with this. What's driving the spreadsheet? No, it's in globe Earth mode. We're fully steel manning.
Okay, all right. Is it also true that multiple Glober methods are represented here, and that at this point I would say it's impossible to strawman the method unless you want to recommend a newly integrated, not yet seen globe prediction method?
I mean, what I like about what we're showing here is that we could do like a sanity check and subtract the difference in true position at time of occlusion from the peak, from the observer's true position. And we could see that the full 360 celestial drop there, which is 360 times the distance over 2 pi r, gives that full angle sweep. So we can see that we're in alignment with the positions of the stars. Time-wise, we're in alignment with the drop of the stars.
Isn't that also confirmed independently in Stellarium as a secondary check for our method quote, which they keep saying is straw manning, but actually gets independently corroborated by Stellarium?
Yeah.
And so it's the same math. Yep.
Yeah, if our numbers don't match Stellarium, then we would probably be, in error.
Right, so it's weird for a person to then claim that we're straw manning the method with a thus far unrepresented globular prediction method, and also that we're doing so by an unannounced, undiscovered formula, and etc. That's just a crazy claim at this point. I'm just saying.
Yeah. All right. Well, the links to the spreadsheet will be over here. So if any of the globe lads would like to go over that, or maybe we made a math error, could use a different formula or something, suggestions are welcome. Here's the error bars.
I'd like to go over something with you, if I may.
26. All right.
Talk about persistence.
All right. Are there any questions or comments?
Yes, I have a comment, and it's about the Blinn Mountain from Edith's Hook location.
Are there any questions or comments from people that are actually invited to the celestial theodolite updates?
Well, you're straw manning my data that I provided. Okay, you're misleading people. So it's.
That's weird. I said that's so weird. I said, are there any questions from people that are invited to participate?
I didn't hear anything, to be honest.
And then the person who wasn't invited was still talking. So weird.
Yeah, we addressed his straw man argument, I think, because there's no way to possibly straw man it. And at this point, if there is a new method, let us know where we are. But these ridiculously vague, just straw man claims without saying, hey, when you're representing the angular drop with your half of the angle arc formula or whatever, then that's not correct. That's one thing. If you're saying, hey, the drop over distance calculator you're using is not, this derivation, it comes out to something different. Great, that's another thing. If you're just saying that with none of those, then we don't care.
And like I said, if there's another formula to use that we should be using, hit us up. Like we'll adjust it. Because the issue here doesn't seem to be the math. It seems to be that the occlusion timings don't line up with the globe. The error is always greatest on the globe side because there was no geometric intersection at the time predicted.
I remember like update 2, 3, and 4, the Globers were like accepting everyone was on board with it. They were excited. No one was teleporting. Everyone was agreeing with it. But then the implications started to set in, and then these ridiculous backwards projections started to happen. And now no one accepts anything about it, which is a weird position because they were all so enthusiastic in the beginning. If anyone remembers, someone should go watch 2, 2, and 3, and 4. Maybe someday Roll My Boulder will have some objections too.
Alan, I was going to say, after these weekly updates, has anybody like reputable or genuine shown up to critique the math and or method, or is it just a bunch of nuh-uhs and the normal people saying nuh-uh?
Dude, all the math fixes and critiques came from people on the flatter side with some assistance on Globe Lads helping out as well. A couple of Globe Lads, but it's mostly been flat earthers who are correcting the math and stuff.
That's awesome.
It's a group effort at this point, but I just want to, the corrections are coming from us essentially. So initial bearings are from my house. I still don't get what the bearing means. It would just be
the direction.
Direction you're facing. I can't pull over any further.
It's a direction. I don't understand. Like what?
Yeah, it just seems to me that this is exclusive, repeatable proof of the planar nature of our realm, and the world hadn't caught up to it yet.
Speaking of repeatable nature of our realm, we have the Celestial Bounty Rewards Program. which I'll put a link to here. If you live in the southern hemisphere, we're in the northern, there with some stipulations, you could earn some money for your recordings. So if you can record the stars at night and a mountain peak with about this quality of distinction of the mountain peak with respect to the blackness of the sky, then you're in luck. You can go to, if you live in the northern hemisphere, if you are, let's see, 300 feet or lower for sea level, or with respect to sea level, then, and you could be up to 10 to 20 miles away from a peak, go get some measurements for us, send us the videos, and we will pay you $50 per measurement. So if you can go, you could do like 20-mile or 10-mile intervals, so starting at 10 miles away and then going 20, 30, whatever. You can record as many videos as you want per night for the occlusions, and you will get $50 per video. For those, we have a $300 pool set up. We haven't had any submissions thus far to claim any of the money. Oh, actually, we've had one, but the guy didn't do it right or something, and the data is, we don't know what time he actually started the thing. So anyway, don't end up like that. So to be clear, we only need 3 things from you to participate. We need the name of the peak that you're shooting. We need your latitude and longitude when you started the recording, where you're recording from. And we also need the time that you start the recording. Most modern recording devices will put the output of the file name as the time that the video was started, or you can do something like overlay the time, like the timestamp on the video or whatever options you have available to you. It's best to just use that and keep it internal. It makes it really easy and airproof. So just make sure your device is synchronized to GPS time, and then have your recording either be in the file output name for the timestamp or have it displayed in the video, and you're good to go. Just send me the video of the star and we're good. All right, and then if you live in the south, it's the southern hemi, any elevation, doesn't matter where you're at, and 10-mile interval distances is preferred. Shoot those peaks in the south and we'll get you $50 per recording for those as well. And then if you want to submit the data, you can email me at allenspaceaudits@gmail.com, and you could use your favorite file sharing upload website. So Dropbox, Google Drive. I like this transfernow.net website. It's pretty nice. And then we will pay you out in Cash App or PayPal of your choosing.
That's so generous. I hope they start rolling in.
Yeah, we had a lad try get us a southern hemi measurement, but his time synchronization didn't work out, I guess. And the video files he sent me were like partial files. So like if you can output it as a single file, I don't know what 524 megabyte files are for. I only know what one singular file of those all added up together in the form of an MP4 do. So keep that in mind. But all right, that's the current state of things. So to quickly recap, we have independently derived error bars now based off of the min-max possible errors that could occur in the measurement, starting from latitude errors all the way up to occlusion timing error, all the way up to possible distance errors. So like min-maxing everything, averaging it out, and then getting the error bars off of that is what drove all those graphs there. And then we converted all the time on the page to real time. So we have real time conversions now for everything. So you can see what all the angles mean in relation to time, because angles equal time. And then we can also found that by judging the intersecting difference between our 2 predictions, we see that the flat Earth is closer than what the globe predicts every single time. All right, if there are no questions or comments.
I guess I was going to ask, how many overseas measurements or reports have you gotten back?
Overseas?
Like
0.
how many are in the States? None from over like any other country?
One in Canada and the rest are in America.
Man, we got to branch out. I'm going to go to work. I'm going to get some people fired up.
Do it. Send them this link for reference.
Yeah, DM me. And And I'll keep trying to figure out the P1000 thing, because if any of y'all are curious, the P1000 has the capability of like syncing to your phone through this thing called SnapBridge, and it's supposed to update its location, lat long, GPS, everything, even altitude, and then that way, when you film with the P1000, you should be able to overlay the exact time, GPS synced time on the video itself, and that would be ideal. But mine was tripping out and having trouble using SnapBridge; it just wouldn't connect to the phone and the app properly. So I don't know if that's a known issue or something shady, but I'm working on a video, or I will do a video if I can get it to work, on how to use the P1000, probably even the 950, 900 series. I don't know anything about the 1100, but yeah. Let me get that link, and then I'm gonna reach out to a bunch of people and just see if we can get a few more from other continents.
Awesome, thank you. Yeah, if we get some more stuff in the south, we can do some continual mapping of the celestial sphere and get some of these rates hammered out for the south.
I mean, dude, this should be. My bad. This should be easy, bro. Like, there's places in the South where $50 American is like, it's like your weekly. You know what I'm saying? It's like your monthly paycheck or something wild. Like, you should be able to get this done.
I was surprised that nobody has. Well, only one person has really tried so far. A couple people have reached out to find out more. Oh, also, if you have a peak, so check this out. Brian made this really cool script for us, which I'll make it available if you guys want to use it too. But what we can do is, if you know the peak and you know whereabouts you're going to be shooting, we can enter the lat long coordinates of the peak and where you're going to be and the time that you're going to be there. And we can get all the stars that will be at that angle relative to the peak over the time or whatever. So you can have like a window of possible measurements or whatever. So you're not just guessing or whatever, if that helps. So we have a whole script for that. Let me see if I can pull it up real quick.
Yeah, that helps a lot. And I was thinking, Alan, a short video on exactly what you want, step by step, and like the $50, whoever, because I want to send folks that are in other countries. Hey, man, just like what Jeremy was saying, like, you have opportunity, $50 American. It's easy. Just do this. They want to see it on YouTube, see the steps. Oh, that's simple, and I can help edit, or even I just don't have peaks around here. I guess I could go through the steps. I know it sounds silly. I could go through the steps on a water tower that's half a mile away to show the setup as if it was a mountain. Or if there's somebody that would do the video, it needs to get done though, because I think that would bring in at least 10 to 18 people to do this if they had that step-by-step guide.
Yeah, for sure. All right, let me give a quick demo of this bad boy in action. So we got peak laddie. Oh, it's already calibrated to Pikes Peak. My freaking guy. So we could just go. Is it on the same? Yeah, it's on the same. So yeah, what you could do, click find star crossing, and then it'll pull up all the stars that transit over the peak, and then hit that angle that's produced by the difference in the distance to the peak and the elevation, because you enter all of that there. So it does all the trig and stuff for you, and then all the stars that cross that, and then it gives you the time. So you can enter a time window here. So you can actually have some a frame of like where to be and when to be there, so you can get the measurements. But yeah, then you'll see our boy 39 Aquarii right here at the time of occlusion. Awesome script, Brian. Thank you so much for that. That'll be extremely helpful. But yeah, if you have a spot in mind and a distance to film said peak from, let me know, and we could set it. I can help you figure out the time. All right, I think we will wrap up this episode of Celestial Theody.
Hey, sorry, I was connected to my phone. To my car? Can you hear me now?
Yes,
I had
sir,
a question. So why does the altitude matter? Because like I'm in Utah and we're certainly higher than 300 feet. What's up with that?
Oh, it was the ratio of refraction at lower when you're low at the sea level. We were wanting to see what the measure, like how that affects things on the celestial spheres. Let me show you what we plotted out, and by we I mean Brian. Let me show you what Brian plotted out here. Is this the one? Yes. Copy image. All right, so this blue line here is the stars following the perfect celestial sphere, and then the occlusions are the deviations from the celestial.
Wait, yeah, you got to share your screen. You got to share it.
Oh, my bad.
You dropped it down.
Yep, I got you.
Sorry, I was talking and you were trying to close out the stream because I was connected to my car, so I caught you too late. Sorry about that.
No, you're fine. You're fine. Okay, do you see this on the screen now?
Yes.
Okay, so this would be the stars following the perfect celestial sphere going down at 15 degrees per hour or whatever, and then this is the deviation that was measured at the time of occlusion. for their geometric angle. So as you can see, for houndstooth, when the angle was 10 degrees, it was high in the sky, the occlusion follows the celestial sphere pretty closely. And then as we get down to these lower angles, there's a lingering. So based off of not just the angle, but the distance to the peak, we see the north peak has like the most amount of deviation from the celestial sphere. And then down here we have Blend Mountain, and there should be the other blend somewhere around here, but it's not on this one. But we can see how there's a deviation from the celestial sphere. So we're just kind of interested in plotting out that relationship of what's going on at when you're below sea level. Because when you're above sea level, you don't get enough refraction to do something like, I'll give you an example here, like this amount of refraction of 25 arc minutes at 52 arc seconds of angle, or no, I'm sorry, 42 seconds of angle is only comes out when you're like below sea level. So we have this weird instance where the refraction correction is larger than the central angle sweep. So just figuring out like what that looks like and like why. So we're just kind of interested in that. So if you're not within that threshold, you're not going to have that type of an effect where the refraction amount or the offset will be that much, because that's where the largest offsets were. So the flat Earth was off by 10 arc seconds here, or arc minutes, sorry, and globe was off by 21. So like the largest discrepancies are in this range. So we're just interested in more data from it. What was your question again? I can't even remember.
Oh yeah, it was just and that's pretty trippy. I was wondering why higher elevations, like why you didn't want higher elevations. That's why.
Oh yeah, because that and pretty much everyone's above sea level, and like so it's like way easier, way more common. We could do a bunch of those, anywhere or whatever. Like it's just more common. So we were trying to get a specific threshold.
Alrighty, well, thank you.
Mm-hmm. All right, well, that wraps up this week's Celestial Theody. Be right back.
I mean, you actually might want to be careful. You let a country like Indonesia get wind of this or something. I don't know how many directs you got back in this $50 thing, but probably put it on Fiverr. You know what I'm saying?
Limited time only.
Limited supply.
Okay. All right, lads, we were wrapped up here in this event. Thank you all for coming out and listening. Much appreciated. We'll see you guys on the next one.